Good evening, everyone. So for the first popular science talk of the day, we have with us Dr. Pallavi Bhat. Dr. Pallavi Bhat is an assistant professor right here at ICTS-Bangalore. Her research interests lie in the fields of astrophysical fluid dynamics and plasma astrophysics. Prior to joining ICTS, she was a postdoctoral fellow at the University of Leeds, and she finished her PhD from IUCAA, Pune. Her talk today is titled A Journey Through the Plasma Universe, where she'll highlight the importance of studying plasma astrophysics. This talk will also weave in reflections of her journey as a woman in science. So let me welcome Dr. Pallavi Bhat. And over to you.
Hello, everyone. It's so nice to be in a room full of women. I have done parts of this talk previously with Miranda House. So if anyone is from Miranda House over here, you will have seen some of this talk. So let me start this journey. So I want to first tell you all a little bit about my background. So I come from a family which has a fairly liberal outlook. Okay, so both of my parents are, they studied till, their masters. One did it in physics, one in math. And so I kind of did come from a family which didn't stop me from doing what I like to do in life, much at least. So I started out as an engineer, and then so I did my engineering from Mysore, and then I even worked for a couple of years, and then I realized that that was not what I wanted to do for a long period of time in my life. So I kind of said that this is, I stop here, I quit that. And then I even, for a while, thought that I'll do something else. Maybe I'll become a journalist or some such thing. And all of that thankfully didn't pan out. And so then eventually I kind of rediscovered physics in some sense. And then it so happened that I got an opportunity at NCRA, Pune, to be an intern there and learn physics. I was learning physics from the master courses at Pune University, which I really got into, and I really enjoyed it. And then that allowed me to, write all these PhD entrance exams and qualify. So then I joined as a PhD student at IUCAA, which is Inter-University Center for Astronomy and Astrophysics in Pune. And then I went on to do a postdoc at Princeton, MIT, and Leeds, and now I'm a faculty member here. Okay. So with that, I now get into the scientific part, and then I'll kind of switch back and tell you a little bit more about my journey and so on. Right, so here I lay out the composition of the universe. In the total pie, the much of the pie goes towards dark energy, okay? And then when you look at what is actually the matter, that again is split into something exotic, that is dark matter, which we don't know what it is. And then the regular matter itself is some 20%. And the regular matter contains of, your stars and galaxies, dust, this, that, everything. And this regular matter basically has all of these astrophysical objects that you might have come across earlier. The sun, stars, galaxies, clusters of galaxies, right? And then this is a picture showing you black hole and a jet emanating from the black hole and an accretion disk around it. Then there are supernovae and so on. So there are all these, interesting objects out there in the universe. And what are they made of? So 95% of this visible universe is actually made of plasma. So that is an important thing, because like whatever electromagnetic radiation that we are getting, we are observing, we are doing all these studies, using these observations, they're all emanating from, objects which are in plasma form. So what do I mean by plasma form? They are at high enough temperatures such that they are in the form of, electrons, ions, and so on. They are in the plasma form. And invariably, almost all of these plasmas host magnetic fields. Now, why do I bring this up? Because much of astrophysics and astronomy is driven by observations. Okay, there is no astrophysics without observations, right? And if you look at any of these observations, you find that there are these large-scale coherent magnetic fields, okay, which is kind of very surprising. So it stands out like a thing, it stands out like a thing to be understood. So these plasmas basically host magnetic fields. So we can start even small at home, that is our own Earth. And the Earth has a dipolar magnetic field, as you can see from the schematic here. Of course, this dipolar axis is not aligned with the rotational axis. It's slightly away, but you can use this magnetic field to actually find your north, because if you have compasses, then that will tell you what to do, right? And have you ever wondered why there is this magnetic field? Is there like a giant bar magnet in the center of the Earth, or what is it that is keeping the magnetic field alive there, right? So that is a question there. And then these are simulations of this magnetic field on Earth. And you can see that actually the simulations show that the magnetic north and south may not remain so. They undergo reversals and so on. So we actually have even, paleo observations. I mean, basically some of these things that we have dug up, and they show that basically there have been reversals in the past. The magnetic field has not always been the way that we see right now. And so this magnetic field in Earth is not static, it is dynamic. So that is the first thing I want to impress upon you. Then we go on to the sun, and you can see like all of these small strands and loops, etc., sticking out. What are these? These are basically, magnetic field lines. And this particular image is in the X-ray, so you can kind of see all of this stuff. Then there are much more interesting things that happen in the sun, which is all related to what's happening with the magnetic fields over there. So if you look at this picture here, that is the visible sun. And on top of the visible sun, there are all these spots, dark spots. They're known as the sunspots, okay? And they're not always there. They come and go, all right? And then if you kind of look at the corresponding magnetogram, you find that these sunspots are associated with really strong magnetic fields. Okay, so these magnetic fields are actually the things that are making the sunspots very dark, because they're cutting off radiation in some sense. And then this picture over here shows you basically the radial magnetic field. If it is summed up along the longitudinal direction, then how that varies over a period of time. And you can see that there is some very systematic pattern that emerges out of this, right? This is known as the butterfly diagram, okay, because of the pattern that you see. So you can see that, there is some movement of the strength of the field going from higher latitudes to lower latitudes and so on. That is associated with the movements of actually the sunspots. The sunspots originate at a higher latitude, and then they move towards the equator and so on. Okay? So this is all to be associated with the magnetic fields in the sun. So you can see that these are really dynamic things. They are not static. Your bar magnet will not do the job. There's something else going on, right? Then now, even more surprising is, having magnetic fields on the scale of a galaxy completely, right? So that is also true. So if you look at radio observations, this is the M51 Whirlpool galaxy. And if you look at the radio observations and get polarization data from that light that you observe, then you can kind of draw the alignment vectors for the magnetic field. Okay, and that tells you that these magnetic fields are like completely aligned on the scale of the spiral arms of your galaxy, which means that these magnetic fields are really big. So again, like what is giving rise to such large scale magnetic fields, right? And similar things are true of a galaxy cluster. In galaxy clusters also you see these magnetic fields. And then also accretion disks, and this you all must have seen more recently. This is the black hole image from our own galaxy's supermassive black hole, and then this, as you can see, is slightly different from this image, right? So it's got these lines. That's again giving you the polarization of the light, which indicates there are magnetic fields around the black hole, right? So these so now we come to the aspect that why should we care about this magnetic field, right? So I've already told you that the plasma universe, I mean, the universe is, much of the universe is in plasma form. So if you want to understand the universe, you need to know about the plasma physics in there, right? Then you also, it is true that, you know, if you have magnetic fields in these plasmas, they give the plasma itself some fluid property. So when I talk about plasma, you are thinking of, you know, like electrons, protons, ions, etc. But, you know, they do have a collective behavior as a fluid, and that fluid property is gained by, you know, having magnetic fields in there, which give them some sort of elasticity. Okay. So these magnetic fields also are important for star formation, can help in tracing galaxy formation, and they are important for accretion disk turbulence and many other important astrophysical phenomena. Okay. And also importantly, in many of these astrophysical systems, where you cannot see in the visible spectrum, these magnetic fields facilitate the emergence of synchrotron emission. What is the synchrotron emission? Basically, you have all these electrons gyrating around the magnetic fields, and as they are doing so, they are accelerating, and so they are radiating. And this radiation is known as the synchrotron emission radiation, and that comes in the radio band of the wave of the electromagnetic spectrum. So you can, what you can't see directly in the visible spectrum, you can see it in the radio. So a lot of your astrophysical objects are to be seen in the radio band. Okay. Okay, so we have been, I have been telling you that there are all these big coherent magnetic fields, and we said that, okay, where do they come from, right? So we said that there's no bar magnet, right? So then how are they, like what is generating them, what is keeping them there? So there is something known as dynamo. A dynamo is a process which converts the energy of the turbulent motions of the plasma into magnetic energy. Okay, so how exactly this comes about, I will tell you a bit more in some time. So this dynamo process is basically keeping the magnetic field sustained over there in all of these astrophysical objects. And then there are two kinds of dynamos, one large scale dynamo and small scale dynamo. The more interesting dynamo, of course, is the large scale one, because that leads to, you know, large scale magnetic fields. So we want to understand this large scale dynamo to understand these large scale magnetic fields, right? But invariably, every plasma system will have both large scale and small scale dynamo, and there are problems related to that, which I'll come to. So I said that dynamo is the guy which is, you know, doing the work of, you know, generating these large scale magnetic fields. Now the question is, yeah, so do we have the free energy to actually get this process going on? where is the kinetic energy of turbulent motions coming from, right? So turns out that all objects are invariably also turbulent. So on the sun, we have all these instabilities like convective instability, which is churning the fluid around. Then in galaxies, at the end stages of a life of a star, it basically goes supernovae, and that is such an energetic process that it will churn up the fluid there in galaxies. Then again, if you go to galaxy clusters, you have mergers of galaxies leading to turbulence. So at this point, you might be wondering, like, okay, all that is okay, but like, what are the equations that you're looking at? How do you study these objects, right? So that's why I want to launch into a small MHT primer. Okay, so like I told you earlier, that magnetic fields give a fluid-like quality to the plasma. So you can treat them as fluids. So if you're treating them as fluids, then what are the equations governing fluids, right? So let's look at that. So the first equation is what is known as continuity equation. This equation comes about due to mass conservation. So this is, okay, I think there's a picture missing. Right. So if you were to just take mass conservation, arguments for a small finite volume, then what kind of equation does it lead to? So on the left hand side, we are looking at how the mass in this small volume changes, which is given by delta of rho, which is the density, and delta x is kind of the size on one side, and A is the area, right? And that is divided by delta t. And on the right hand side, we have mass flux into the volume minus the mass flux out of the volume. Very natural argument, right? So that will tell you how the mass is changing within the volume, right? So the mass flux into the volume is given by rho into v, velocity, into area, okay, minus these updated quantities at the point where things are going out, right? So if you do all of this, you will cancel out some of these terms, and then you can see that basically if you bring this delta x here and then take the limit of delta x and delta t going to a very small value, then you will arrive upon the continuity equation. Okay, so that's your continuity equation. And then you can do a similar thing with momentum flux density, flux density. So if you take basically the velocity of the flow, and then if you do the same kind of calculations, exactly the same thing that I did with mass, if you do it with momentum, you will come upon the momentum equation. And on the left, this is basically a force balance equation, right? On the left-hand side, you have all these acceleration type of terms. And on the right-hand side, you have all these forces which are acting upon the flow, making the flow move about, right? So there is pressure gradient, which can make the flow move. And then there is viscosity term, and then there are other forces that you can account for. Now, all the very interesting turbulence kind of phenomena that you see in this is coming about because of this crazy nonlinear term, v dot grad v. And basically the question is that how significant is this term? So that is codified by what is known as Reynolds number. So that gives you basically the ratio of this term to a viscosity term, and that tells you that if you have very high Reynolds number, that will lead to turbulence. Okay. Now, the last equation, my favorite equation, which is the induction equation, because it tells you what is happening to the magnetic field in the given plasma, right? So here we call upon Maxwell's equations. So you have Maxwell-Ampere's law, which you might have come across in your B.Sc. etc. And Ohm's law that tells you that if there is some current going through a certain medium, it will face some resistance. That sigma is your inverse of resistivity, or it is by itself, it is conductivity. So you take these two equations, eliminate J, you will get an expression for the electric field, right? And then you bung that into the Faraday's law, you will get a dynamical equation for the magnetic field, okay? And now this is actually quite similar to momentum equation in some interesting ways. But again, you have this eta term, which is killing the field. And then there is this term, D cross B, which will do various interesting things, including the dynamo action that I was talking about earlier. So if you have the fluid moving in some very interesting fashion, it can do things in such a way that the electric field due to this term is basically in the same direction as the magnetic field. Okay, not the electric field itself, but the curl of the electric field. And if that is true, then you can have a growing magnetic field. Okay, you can have growth of magnetic field. So now, if we come back to the momentum equation, there will be the force here due to the magnetic field known as the Lorentz force. Now, in totality, with the continuity, momentum, and induction equation, we have magnetohydrodynamics. All right. So with that, I will stop with the mathematical framework. Now I will go on and tell you about all these problems that I dealt with. There's something called the small scale dynamo. I was telling you. So what is the small scale dynamo? So when you are churning the fluid, you are putting energy at a certain scale, okay, at a certain length scale. And if you happen to grow magnetic fields on length scales that are smaller than the energy carrying scale, the one that you are putting in, at which scale you're putting energy into the system. So then it is known as a small scale dynamo, because it's all on scales smaller than the energy carrying scale, okay? So as you can see that to start out with, it kind of was like all on very small, tiny scales, right? But eventually it kind of grows over a period of time, and it actually grows also slightly over the length scales and so on. But it is essentially, there is no large scale field or there's no mean field in this process, right? So this is an interesting problem. And this was already actually posed and solved in 1965. So like, what is our job then? I mean, like, the problem is solved, right? But not quite so. We know only the kinematic part of the problem. So what do I mean by kinematic? So you can think of this as some sort of instability, right? So like I was telling you that there will be a Lorentz force in the momentum equation, which will back react on the flow, right? So this magnetic field is growing and it becomes very significant in strength. And then it kind of it forces the flow itself. So until the magnetic field becomes very important, the flow is doing its own thing. Okay, the field is not interfering, it's not doing anything to the flow, right? Yeah. So, but once it becomes important, then it kind of kicks back on the flow. So you go from kinematic to the saturation regime. Okay, so the kinematic regime is the linear part of this problem, and the saturation is the non-linear part of this problem. So the linear part is solved. Okay, so the non-linear is not. I mean, it's hard. Then here is our large-scale dynamo. So now you can see that there will be. Oh, what happened? Okay. So now you can see this is a different kind of flow compared to the previous one. But now you can see there are huge patches of magnetic field. And eventually what happens is there is this very large scale pattern that comes up, right? So that is your large scale dynamo. It's basically bringing out a turbulent magnetic field, which is coherent on large scales. Okay, so here basically the problem is that if you so most of the astrophysical systems out there are really large magnetic Reynolds number systems. okay, which means that the resistivity is very tiny. If any of these processes are controlled by resistivity, then it is hard to, expect really significant magnetic fields by end of this whole thing, okay, on, the astrophysical time scales. So this is the major problem. Can we really have like a fast dynamo? Can we really have like a large scale dynamo operating on fast time scales? Okay, so that is the large problem in this field. So my PhD work, which was a combination of analytical and numerical work, one thing that we did was to generalize the cousin-Save equation. So I told you like cousin-Save had solved the problem exactly, but he was able to do that because he used a very special condition. He said that the flow that we are dealing with should have no memory effects. Okay, so that is why he was able to make progress, and he solved the problem right in 1965. But real flows are not memoryless. They have some finite memory effects. So what we did was to include some finite memory effects, and we generalized the cousin-Save equation. Then we also apply the small scale dynamo to understand observational signatures that we see from galaxy clusters. Okay, because galaxy clusters don't have rotation and do not have large scale fields. So we think that basically galaxy clusters have very small scale fields, and that is what we have tried to do here. And then the other interesting thing that we did was to actually build a unified perspective for looking at the small scale and large scale dynamo. Okay. So now I come to the part where, I tell you like, how was the PhD for me, right? It was in one word, very, very good. Like it was great. Okay, I really had a good time. Otherwise, I would not be here, right? So what made it work, and what did I not do, and like some of these things are what I want to discuss with you here. So one thing is, I tell everyone more than anything else is that please find a great supervisor. I know it sounds like, like how do you do that? But do your homework when you do go to a particular PhD like place, when you're applying for PhD and so on. Look at who they are, talk to their students, postdocs, etc. Okay, if you can even talk to them directly, do that and get a feeling for what it is, and so definitely do that. I mean, I am not saying that you'll always, I mean, I'm also not saying like like half of them are bad or some such thing, but like the relationship that you make with your supervisor is important. So keep that in mind. Okay. Then the next thing is that I feel that I didn't do enough of. So I got into nitty-gritty of every other project that I did. But the one thing that I didn't really do during my PhD, I feel, is that read a lot of new papers. Okay, I did read some, but not a lot. So I think PhD time is you have so much time at that point, you can actually do these things very rigorously. So, you will not get that kind of time later on in life. It gets harder and harder. Okay, so, so do read new papers and make a lot of notes, be very organized in all of this, because it's a long, it's a marathon, right? So, so whatever you do now will help you later. So be very organized and so on. Then learn as many techniques and methods as possible, because you're a student, you can absorb more at that point. So you want to do all of that. And yes, you can marry and start a family during PhD, and probably it's not a bad time to do that. Okay, because it gets slightly harder later on, but I'll tell you why, because once you start doing postdocs and so on, you're moving around the place and it might get harder. But if you wanted to do that, you can. It is not to be like thought too much about, okay? At least in the 5-year programs. So next topic I want to hit upon is magnetic reconnection. I'm coming to this because this is the stuff that I did during my postdoc. Okay, so that was a good thing that happened to me. I didn't simply continue doing dynamos in my postdoc also. I changed topic in some sense, and I really, to be honest, I got the opportunity to do so. So change topic in the sense that it is a subtopic. I mean, it's a subtopic in plasma astrophysics. It is not like an entirely different field altogether. It's just a simple subtopic which is different, okay? But it has a lot of literature associated with it and so on. So if you do get to work with somebody who, you know, introduces you to a new topic in your postdoc, it's always a nice thing because, you know, you learn a lot more, you diversify, you expand, and that's a great thing. So here what is happening is that basically there are these field lines which are coming towards each other, and they are meeting at this point where there is a current sheet, okay? And what the current sheet is allowing the field lines to do is to break and reconnect. And when they break and reconnect, the reconnected field lines move out of the current sheet as an expulsion. Okay, so this is known as magnetic reconnection. So here I have essentially these solar flares on the sun. And we all think that, okay, so where is magnetic reconnection important, right? So it is important in many different contexts. It's important in astrophysics, of course, but also in space physics, also in laboratory physics, because the fusion plasmas, they have to deal with magnetic confinement, right? So you're doing all your fusion experiments inside something, but inside what? Inside some magnetically confined thing. So if this magnetic confinement is held together by all these strong fields, you don't want the fields to get disrupted. But the very first thing that can happen is what are known as sawtooth crashes, which are driven by reconnection. So in fact, much of the reconnection progress has happened due to plasma physicists who have worked on fusion. So in fact, when I went to Princeton, I was working at PPPL, which is Princeton Plasma Physics Lab, and all of them knew about reconnection, and it was an important topic over there. So that is how I learned about it. Also not just at Princeton, but mainly at MIT. And here in this particular case, I'm showing you an application that is related to the sun, right? So there are these solar flares that are taking place on top of the sun. And what is happening is that, okay, maybe the video will tell you a little bit, but before that, maybe I should give you a small picture. So like I was showing you that there are all these magnetic field lines associated with the sun. So they're coming out of the plasma surface, they are coming up. And as they come up, they are carrying the plasma along with it, right? All the material along with it. And then what happens is that, I mean, why do they come up is the first question you may ask. And that is essentially because, you know, these magnetic field lines are buoyant, and they have, I mean, even if they are in pressure balance, the amount of material inside the magnetic field is much smaller compared to the material outside. So they come up, and as they come up, they carry the material. And then what happens is that these field lines themselves interact with each other and lead to magnetic reconnection event. And then as a result of this reconnection, they throw the material out into the space. And it goes out into space, and it actually streams towards us, right? It streams towards Earth. And that is what you will see in this small video that I'll show you. So I can't make it full screen. There's field lines coming out, and now you'll see that it kind of pinches off because of reconnection, and then it travels towards Earth. And remember, Earth also has magnetic fields. And so the field lines which are associated with the stuff that has been thrown out of the sun then interacts with the field lines of the Earth, and then it leads to reconnection again, and all that material which was there coming from the sun is now come and is come into traveled along the magnetic field lines of the Earth, and they get concentrated at the poles, and then they interact with the atmosphere near the poles and then lead to aurorae. Okay, so you must have wondered, how do you get aurorae, right? So now you know the answer. And what is the answer? It is magnetic reconnection, okay, which is leading to all of this. Yeah, sure. By the way, you want to stop me at any point if you don't understand something. You didn't really stop me, so I think you understood everything. So yes, so that stuff came and it's interacting with Earth's magnetic field, and that leads to reconnection. All of the material travels towards the pole, and then you get all of the beautiful stuff that you see. If you go to Iceland, apparently you can see that that was supposed to be a trip that I was to take and didn't happen. Guess why? Yes. All right. Okay. Yeah. So that's basically the plasma from the sun, which is getting, so the sun is made of plasma, right? So all electrons, ions, and so on. So yeah, it is matter, and it's those charged electrons and ions, charged particles are streaming towards Earth, and then they come and interact with Earth's atmosphere and the molecules in Earth's atmosphere, which leads to aurorae and so on. Yes. Yeah.
I think my question is similar to what ma'am asked earlier. So the lines that we were seeing, they were actually the representation of magnetic lines, right? But now that you have answered, I feel that it's actually plasma that is going, not a bunch of magnetic lines. It's plasma that is going, holding the magnetic properties.
Right. So like it is actually plasma, whatever, the plasma material which is being thrown out of the sun, but it is associated with those magnetic field lines, which are enabling this whole event to take place, right? I mean, if you didn't have any magnetic field lines associated with it, you won't have reconnection. And then all of that will not travel towards Earth, etc., right? Because it's not getting thrown out in that sense. So yes, so like that is my contention. Okay, from the beginning, that is what I have been trying to tell you all, that because the universe has all of these astrophysical objects, which are essentially made up of plasma. So there are all these magnetic fields associated with the plasma in all of these astrophysical objects. Okay, and then the question is, how do you keep these magnetic fields in there? Because see, the universe that we are observing is at current epoch is I mean, even if you see the local universe, etc., it's basically at an epoch which is much after all your Big Bang and expansion of universe and reionization, everything has happened Okay, so it's that point you're seeing. So clearly the fields have existed for a very, very long time, right? And why this is surprising is that actually, if you look at the induction equation, which I had shown you earlier, right? So there was a term which was killing the fields. And also, if you have turbulence in the system itself, that will also kill things. So now what is turbulence, right? So turbulence is something that is like a double-edged sword, or it's something that's both good and bad, right? So turbulence can transport things around really fast, but at the same time, it can kill things really fast, right? So like the classical example for turbulence is that if you have like if you open your a perfume bottle on the side of the room, and another person is standing over there, then that person gets to smell the perfume only like maybe like 5 minutes later, right? Because maybe the air in the room is very still. But now if you turn on the fan, then if you again do the same experiment, the person on the other side of the room can smell the stuff immediately. But at the same time, the whole thing gets dispersed away very fast. But in the earlier experiment, you could have probably smelt it for a longer period of time, right? So that's the thing about turbulence. So it'll do both. It'll kill stuff, but it'll also efficiently transport things. So Dynamo again is a similar thing, right? So so the underlying turbulence in the plasma is growing the field, but it's also killing the field at the same time. But it's actually the growth which wins over the killing by like a little. And that little is enough because this is an exponential process. Okay. So if there was no dynamo, you will just simply kill the field, and the magnetic fields will not exist. Okay, so that is why it is surprising that the magnetic fields are out there and they are there in their full glory. I mean, because why should they have been there in the first place? Not necessary. And the reason is that, you know, you have all these turbulent dynamos going on, which are maintaining the field, right? So coming back to reconnection. So reconnection has, in the recent times, also come in a big way. Yeah. Was there a question? Okay. So reconnection also has come in a big way in recent times to kind of explain very interesting things like, you know, so like a lot of these plasmas, right, like in galaxy clusters and in many of these high energy systems like jets, and then also in pulsars and so on, accretion disks. All the plasma that you look at is actually very high energy. There are all these particles, these charged particles, which are very energetic. So the question is, why are they so energetic, right? What is the process which is accelerating these particles? So, well, traditionally, there are all these acceleration mechanisms which was proposed by Fermi, Enrico Fermi, known as Fermi 1 and 2 and all these processes. And typically people think that, you know, if there are shocks in the system across the shock lines, you can have all these acceleration, etc., take place. Okay, so you kind of zip the particle along an electric field of some sort, and it accelerates the particle, right? So turns out that magnetic reconnection also can do something similar, because you remember that there is a current sheet at which along which the magnetic field lines interact, and that current sheet has some electric field associated with it. So you can accelerate all these particles along these current sheets and so on. So one of some of the latest things in magnetic reconnection is to also do like all these GRMHT simulations or GRPIC simulations looking at environment around black hole, because there are all these observations which are very interesting, which show like, these hotspots around black holes and so on, all these transient activities, but also some really high energetic events and so on. And the idea is to use magnetic reconnection to try and understand those events, try and see if that explains, the kind of radiation that you see from those objects. So this is a particular simulation from Bhat and others. Here, what's happening is that there is a central black hole and there's an accretion disk around it. And basically what's happening is that there is mass accretion going on. And at the same time, it is giving rise to all these current sheets and leading to reconnection and so on. So this is a simulation showing this one. All right, so at this point, I want to just briefly touch upon the kind of postdoc work that I did. So the first postdoc was related to looking at Dynamo in accretion disks. Okay, that's a very special system. It has a certain instability gives rise to turbulence, which leads to the high mass accretion rate that is required to see the kind of really large luminosities that emanate from black holes in the center of accretion disk and so on. So it's a very special system, and this special system also has dynamos. Okay, and it is important actually to have dynamo because the jets that you see coming out of these systems, right? And these jets are there everywhere across all these accretion disks that you see in the universe. So these jets have to be need like a facilitating thing. So you have some kind of magnetic field funnel, which is allowing the jets to go out, okay, as an outflow. So you need magnetic fields in accretion disk. So I studied dynamos in there. Then there is this latest thing known as plasmoid instability in the reconnection field. So the plasmoid, so the reconnection, the first model for reconnection was again way back in 1956 or whatever, given by Sweet and Parker. And that was a steady state model which didn't quite explain the solar flares, etc., that you see in the sun. Okay, so what do I mean by that? I mean that the solar flares happen on quite a short time scale compared to what the calculation gives you. Okay, that particular model gives you. Then for a longest time in the community, they've been trying to find something that will give you like fast reconnection. Okay, just like we wanted fast dynamo. All of this is because that eta is very small. The magnetic Reynolds number associated with all these plasmas is very large because Rm is some VL by eta, right? So that is the sticky point in all of these processes. So I studied reconnection, the plasmoid instability in what is known as semi-collisional regime, so which was applied to understand laboratory experiments. Then we also looked, so there was also this very interesting phenomena of inverse energy transfer. So usually if you dump energy into a flow, it will travel down the scales, like the flow will break up into smaller and smaller scales. And at some point it will like get dissipated, right? But there are situations in which you can have flow going back up to larger scales. Actually, large scale dynamo is something like that, right? Because you are getting some large scale structure. You have all this turbulence, all this chaos, and out of that emanates a large scale structure. So how, that is very, very interesting and still quite unsolved. So, so we try to provide reconnection as an explanation for the inverse energy transfer and decaying MHT turbulence. So that is the other thing that I did. And again, now let me come to the part where I say like what was good and bad, etc., about postdoc life, right? So I should say I really enjoyed it, but I also really intensely disliked it. Okay, so it is both. So why do I say that? Because the good things were really good and the bad things were really bad. Okay, so at least for me. So I want to like tell you about it, because if somebody had told me all these things, maybe I would have been better prepared for it. Okay, so the good things were that you get international exposure, you meet people. And the very nice thing was that I went to Princeton, and the very next month they have a Dynamo conference. So I'm like Dynamo expert at this point, right? So it was very fun to because interact with people, because I knew something now and I could say things. Okay, so it was nice like that. And then of course you end up learning different research culture settings and so on. So it's nice to see the differences between India there, like the same things and different things, etc. So all of that is very interesting stuff. And then of course you meet different researchers, and invariably actually it was very nice. I don't know if this is a common thing for different people, maybe not, most likely not. But at least in my journey, I met women researchers. The first person that I worked with was a woman. So it was a nice thing, yeah, I had not like closely interacted with women before that. That is the other thing I wanted to say in PhD slide. So during my PhD, I did not have women, what do you say, women grad students around me, because we are always running in some minority. So please, you all please join PhD so that you can, like be there for each other, right? So it was hard for me to find people to talk to who were at the same level as me. Yeah, so because you can keep talking to your advisor, but you are not talking, the advisor is talking to you, right? Like it is typically a one-way flow. It is because you don't know anything and the advisor know the whole world. So it's not, yeah. So you want to find people around you whom you can talk to, right? So that actually happened in my postdoc. So that was very nice. And yeah, you learn new things. I mean, I learned all this reconnection, accretion disk MRI, etc. Then the bad things, of course, is like I was jumping from one postdoc to another postdoc. For these postdocs are like for what, like 2 years, 3 years. In my case, the first postdoc was actually 1 year, and so on. So it is kind of, I mean, initially you are extremely energetic because you're doing new things, you're doing exploring new things. But my postdoc went on for like about 3-4 years, and I was fed up. So like, yeah, because from 2015 till 2021, I shifted house every single year. Okay, and why did that happen? For various reasons. Because okay, one, I went from Princeton to MIT. I was there for three years, but the first year I was at a house which was very far from the university. So then the second year I shifted, which was closer to the university. And then the third year I was going to leave. So at some point there was a little bit of an extension provided. So I shifted again. And so all of these things happened, right? So there are all these very dynamic things happening, and it is all very unstable. Unstable in the sense that it's just a lot of flux, right? So there's a lot of uncertainty associated with it. Then, of course, cultural adjustments. For like, I've had like weird experiences. You can ask me later. So, right. So, of course, the one very typical thing that I found was that, if you go to the US, they are very happy people, right? They're walking by and they are just like, how are you? And so on. And I'm like launching into how am I? And they have got like walked past me by that time. And then I'm like, oh, okay. So, and you think you will get used to it, but every time somebody says, how are you? And they don't wait to hear, how are you? It hurts a little. Okay. So that happened. And then of course, yeah, I think very difficult is, like being really far away from family and friends. And I am really not a phone person. I cannot do long conversations on the phone with my family and so on. I'm like, I'll give you short detail. Like I'm more physical one face-to-face person. So it was hard for me to kind of, like keep in touch properly and so on. So all of that is a part of the postdoc life, but it is what it is. So then, of course, my partner, he was, I was in one corner. He was in the US, thankfully, but he was in the other corner of the US. He was in Seattle, I was in Boston, so we would meet every 2.5 months and so on, or some kind of time scale like that. So it did make those meetings really nice. Okay, so maybe it was a good thing, I don't know. So, so we didn't fight too much, I guess. But long distance is not easy. I mean, you will fight on the phone invariably. So it's so it's hard. It's hard. So all of these things were really, really hard for me. And plus, COVID came and hit us, and so on. So I would advise that, like don't be like me, and like you should. I didn't intermingle too much with people because I think I got like too carried away with my work and so on. But mental health is a thing, and be careful. And so now I'm a faculty member here. And now I currently have, so I joined in 2021 Janish, and since then it's been 2 years and so on. The nice thing about COVID was it sent some really good people towards us. Okay, so I'm very happy with the postdocs and students here who are working with me, because they were like really great people who has joined my group, and I am happy for that. And then this being a faculty member allows exploring my interests with greater focus. And the one thing that I kind of said that I will do when I become a faculty member is to start an international forum. This was also kind of, triggered by the fact that we were living COVID life and we were all very isolated. So I said that I will make a forum for international forum for women, because during my postdoc life, I collected all these people, right? In the sense that, I mean, I didn't necessarily keep in touch properly, but, or at all. But, like the point is that, you meet all these people, you learn about their work, and now you know of them. And so then it becomes easy to do something like this at this point when you have a list of people that you have come into contact with. So then I did this, and I started what is known as a forum of women in astrophysical fluids and plasmas. This is the website for it. ICTS helped me to build it. And so now we meet every month, once in a month, and we talk science. We talk about, we talk like maybe 70% science and 30% or even 20% what's ailing us, what's ailing you, what's ailing me. It's a safe space of sorts, right? So and it's also nice because, invariably what happens with women is that they are in, a male dominated community in science. And so like if you are attending talks and so on, you feel afraid to ask questions, etc. I think this forum is nice because it encourages to ask questions. We hold talks and so on. So it does that in a very free manner. Okay. And so now I come to some general pointers. I've been throwing pointers and pointers. But anyway, I thought I will be as exhaustive as possible. This is one opportunity that I got. So I said, okay, I will say all that I want to. So yeah, I think the single most important thing on this list is the very first point. Okay, because I find that, what happens with women is that we are in our own bubbles, own spheres. We do make friends, but somehow we don't really work with our friends. We talk about everything else, but except work, which makes sense, okay, because they're friends. I mean, it's for fun, right? But it's because we are social animals. Actually, if you form groups and learn stuff together, you retain things much more efficiently. So collaborate, get together, and form groups already at undergraduate level. Just do things together, and you can make it very efficient if this all works out. The other next thing is, of course, there is something known as imposter syndrome. You must have come across it. During your whole journey, you might very well experience it. I think almost it's not actually it's not just one gender. Like, I think everybody goes through imposter syndrome if not invariably, maybe they do. Like, people do. It's not just a woman thing. It's also like men. Like, they also go through these things. Okay. And because of this, you may feel disconnected, you may feel like you are not belonging to this community, etc. And that should not happen. Build bonds, talk to people around you, pay attention to mental health. It is a real thing. It is not just ye mental health problem kya hota. I really had a friend who she and I went through all of her problems together. And while we went through her problems together, she was always like, Pallavi, what is this mental health thing? I mean, like, why, how can stress cause problems, right? And no, it is a real thing. It causes physiological problems, actually. It can manifest in some physical ways. And so you cannot, ignore that altogether. So you have to be happy. Well, all right, you have to make yourself happy. And so that you have to be careful about. And then, the one thing that I want to tell is that, mistakes are common, okay? And do not beat yourself up for it. And, you'll always meet people who will make you feel that your mistake was huge or big or something. Don't allow that. I mean, just let it go. I mean, and move on, because life is so much more. Life is not finally just a PhD, academia, It is everything else also. Okay, so do not beat yourself up on anything. And yeah, form peer support groups, safe spaces, share good practices. Then when you finally go up the ladder, pass it down, help the people who are starting out, give it back to them, and so on. And another thing that I think is very important is you should take genuine interest in the research other people are doing around you. That will really help expand your horizons, give you a big picture of everything. You may not really see a value in it just by these words, this sentence, but there is some value to it, which you will realize by yourself when you do it. Okay. And this is something that I've come across often. So people have told me, and I have experienced, maybe not so much because I'm kind of, like I can be sometimes loud and so on. So, women are ignored in a discussion sometimes because they are in minority. Either like 10 men, like 2 women, it can happen, and it is not like it happens on like purpose, right? It happens like, in a by the way kind of a fashion. But don't feel bad. I mean, just persist politely and, get your point across and so on. So don't be like, they are targeting me or something. Don't take it like that. Just be aware that these things happen, and everybody has all these implicit biases. Women have, men have, everyone has it, and then that leads to much lesser citations for women. So that is a problem also. These are things you can't really control that very much. It's a general culture thing. And just hope for the best and talk to people. Say that, hey, I've done this thing. Maybe you want to look at it. And yeah, very important is, see, all these other things are the workplace related stuff. But the more important things are actually the stuff that you are connected to so intimately, like your family and your, partner and so on. And that is the stuff actually more than anything can pull you down. Because, families, India and, like how people are can be very conservative and so on. So you kind of come across, yeah, in 2 minutes, yeah. So, you can find all sorts of pullbacks and so on. So I would say fight for yourself, not fight for yourself, like think for yourself, like put yourself forward, okay? Don't put yourself at the end of everything else. Don't say this person, that person, this person, and then me. Like, no, put yourself up there, okay? Because you are the person who can take care of yourself the best. So that, and so find partner who will split chores equally, okay? I mean, they say find partner for love and all that, but also splitting chores equally. And later on in your life, when you come up, help other women, make policies which help other women, okay? With that, I end the discussion. So yeah, I will take questions now.
Let's thank Dr. Pallavi Bhat. Maybe you can take 1 or 2 questions right now, and there'll be an interaction session from 6 to 7, so you can ask further questions later. So yeah, questions, anyone?
Yeah, I think most likely they are. So I can pass the link to you. Yeah. Okay, yes. So what happens is that if you have like a compact object, which is really massive, then it kind of pulls the matter around it. But typically what happens is the matter is in some kind of orbital motion. So it has to lose angular momentum to travel towards the center. And in the process, it forms an accretion disk like that. So it's just a disk around a black hole or some other compact object. Yeah.
I didn't exactly understand the magnetic pole reversion. Could you please explain that?
Yeah, so I was telling you that, the magnetic fields are being maintained by a dynamo within the core of the Earth. So in the core of the Earth, there's molten iron, which is the guy the plasma there, which is doing the work. And so what happens is that since this is a very dynamical process, and like I was showing you, like even with the sun, the sunspots are traveling from higher latitude to lower latitudes and so on. Similarly, in the Earth's dynamo, there are these events which take place over a long period of, there's like a periodicity associated with this dynamo. So in that period, in that process, it basically goes from one polarity to another polarity, then comes back and so on. So, but it does that on a very long time scale compared to human life. So like 1 lakh years or so. So you don't have to worry about, the magnetic flip at any near point in time.
All right, then let's thank Dr. Pallavi Bhat once again, and she'll be available for the interaction session from 6 to 7.